the global non-hydrostatic atmospheric model MPAS results from variable resolution mesh tests.
Okay, thank you. I want to briefly show some results from testing we've been doing with a non-hydrostatic global atmospheric model MPAS on variable resolution meshes. And what I'm going to say is essentially going to probably reiterate and reinforce some of the conclusions that Mark Taylor gave us a few talks ago. When we look at how our models perform on these variable resolution meshes, it turns out that, at least in terms of the dynamics, it's very much a question of how you work with your filters. Many of you were probably here yesterday morning and heard Todd Ringler talk about the ocean component of MPAS. I'm going to talk about the atmosphere component. The ocean and atmosphere component share essentially the same, all the infrastructure of the mesh, and actually it's run out of the same driver ultimately. But we are in NCAR responsible for development of the non-hydrostatic and hydrostatic atmosphere components, and the group down at Los Alamos, led by Todd, is working on the ocean model. The MPAS models live on this Voronoi mesh. Many of you have heard we're using what's nominally known as TRISC, although the group that developed it didn't come up with the name. I think it came from somewhere else, but that's what people are calling it now. So essentially, we've got a C-grid discretization on these Voronoi meshes, these nominal hexagons, and most of TRISC really boils down to how do we diagnose the tangential velocity on this face and then use it in our finite volume discretization. Our particular atmosphere model, we very much are attracted to these unstructured meshes because it allows us to introduce a local refinement in a very clean way. And our main applications are, as you might imagine, weather prediction and regional climate, where we want to get down locally to higher resolutions than we currently can afford in global models and get around some of the problems with traditional grid nesting that's often used in global models today to get to regional scales. In terms of the solver, and don't worry about the equations, essentially the big thing to note is that, as you probably are aware, in the TRISC formulation we're using this vector invariant formulation, so we no longer have any nonlinear transport term associated with the horizontal momentum. And in this case, we're also using a height coordinate as opposed to, for example, a hydrostatic pressure or mass coordinate that's often used in many of these formulations, even in non-hydrostatic models. In terms of time integration, we're using a Runge cut approach that also splits to handle the horizontally propagating acoustic modes with a shorter time step. And we do the vertically propagating acoustic modes and the gravity waves implicitly in the vertical to get around the time step restrictions associated with the very high vertical resolution relative to our horizontal resolution. So that's about all I want to say about that. Essentially, in thinking about these variable resolution meshes, essentially our motivation with an MPAS to go to these very smooth conforming meshes, and note that this picture here I have is one of these, and you can see the transition is very smooth, is the one nice thing about the MPAS is that our mesh effectively looks the same everywhere. It's conforming, so our solver, it just knows it's on a cell and it has to solve for that cell, and it doesn't worry about it. It knows where its neighbors are, and there's no hanging nodes or anything associated with any non-conforming refinement. Our scheme is nominally second order, so that the smooth mesh transitions essentially hopefully minimize any accuracy loss in the numerics associated with that transition. And also that the smooth mesh minimizes wave reflection problems at where this mesh density changes. And I want to talk a little bit about that because I think that's the key. Essentially, if you think about a smooth transition as opposed to a very abrupt transition, in the smooth transition, you're only essentially halting or perhaps reflecting just a few wave numbers as you move from as a disturbance moves from the fine to the coarse mesh. So our filters are very efficient down in this wave number regime. However, if you have, for example, a 2 or even higher density change in the mesh, across that transition and it's abrupt, then effectively you're essentially cutting off the representation of half your wave number space or even more, and you're cutting it off in a region where our filters are perhaps not very efficient in removing it. So that's why we like the smooth mesh transition. In practice, I think it will turn out to be that smooth mesh transition may be even more important in allowing us to develop parameterizations, essentially the physics, that will allow us to transition across those scales. It may be even more important there. And I'm particularly thinking in terms of the convective parameterization when we go from unresolved scales to where we permit the grid to resolve it in a non-hydrostatic regime. I think the smooth transition is going to help us a lot. Okay, so as I mentioned, filters are everything, I think, in this. And essentially, there's a number of things that you can think about as filters. In MPAS, there's, of course, some damping from the time integration scheme. I think that's relatively small. You've heard Todd and others this week talk about this anticipated potential vorticity method, which is good for entropy, but we're down in the mesoscales of the atmosphere, and it really is an energy cascade we have to worry about, so I don't think that gives us much. There's some upwinding in the transport scheme, but note that we've gone to a vector invariant form for our horizontal momentum equation, so we no longer have a transport term that could potentially give us some filtering there. We have a few other filters floating around, but basically most of the energy dissipation in the model, if you diagnose it, comes from either some sort of diffusion or hyperdiffusion operators that we have available, a del squared and a del fourth, or a Smagorinsky formulation, which we also have variable, where essentially in the second order formulation now the eddy viscosity is a function of the deformation times a few constants here, which I'll get to in a few moments. Up until recently, we've been mostly in our non-hydrostatic model doing what I would call NWP forecasts, or even longer, over a year or two, regional climate forecast testing. We've been using just the Smagorinsky, and I want to show you some results with that later. But essentially what we're trying to determine is what combination or what filters will work for our applications here with the MPAS numerics. So one type of test we've been using uses the Jablonowski and Williamson jet. Instead of using the impulsive start, we actually use the normal mode initialization. We grow the normal mode. It turns out that the fastest growing mode is wave number 9, and that's what we use here. So it gets us around essentially the impulsive start. But it also, in terms of introducing a variable resolution mesh, we can use that wave number 9 symmetry to perhaps identify where potential problems are as these baroclinic waves, the 9 of them, travel around the mesh and in and out of the refined mesh region. We're going to look at a few meshes. One, what I'm labeling this TR10 mesh, which has a very smooth transition. And here's a density function that's used to generate that mesh, and it has a certain width. Also, one that has a much more abrupt transition, which essentially that transition width is about a quarter of what the other transition width has been. In terms of the filtering, we're doing things a little bit differently than what Todd mentioned yesterday and what Mark mentioned this morning. We're actually scaling the filter coefficients, either the second or fourth order filter or the Smagorinsky, relative to the mesh spacing here as a squared for the del squared, or to the 4 with the del fourth, as opposed to a power of approximately 3. Our reason for doing that is we want to effectively damp the 2 delta waves at the same rate on anywhere on the mesh, the 2 delta waves locally. So the 2 delta waves on the coarse or fine mesh are being damped by the same amount, same amplification factor, no matter where you are on the mesh there. So we're going to look at the results from some of these tests using this scaling of our coefficients. So here's what we're doing is zooming in on those baroclinic waves, and now it's not on the sphere that is plotted on here, but this projection here. And what we're seeing, here's the cold front and rising motion along the cold front. This is the vertical velocity at 850 hectopascals. That's about 1.5 kilometers up, so it's down very low. And we're seeing the rising motion. If it was moist, there'd perhaps be precipitation clouds up here, and the sinking motion behind the front as it wraps up into these baroclinic waves here. We're seeing 3 of them. And what I'm showing here, the refinement region is essentially the middle third of these plots here, and that's where it'll be here on out for this test cases. Here's at day 5 and day 7, the vertical velocity down low. There's not a lot to say here. If you look at the variable resolution mesh, you can see some small differences in structure, but those differences are relatively small, and perhaps a little bit less outside in the coarse resolution region. This here is a single high resolution mesh that you can compare this with. What's interesting, though, is when you look up high, you can see significantly more differences. These should, as you note, these all look the same as they should. Here, at the higher resolution region, there is certainly more structure than we see in the single high resolution region, which may reflect some issues with the accuracy of the numerics or some other things in terms of the transition region. But interestingly enough, we see some fairly good structure out here. But this solution is not terrible, but it certainly is. There's quite a lot of structure in it, but this is very small amplitude. So up at 200 hectopascals, we're looking at 11, 12 kilometers up. These amplitudes are very small, and essentially we're seeing gravity waves propagate vertically off of the frontal structures that you see down here. The resolution is fairly coarse here, so I'm not sure that some of these aren't numerical artifacts. As you get to higher and higher resolution, it helps to go to higher and higher vertical resolution, and we haven't done that. We've kept the resolution relatively coarse. This is 33 levels, but what we're looking at here is to see, do we reproduce the high resolution region here inside here? And the answer is, well, in part, but we're certainly seeing a little more structure, and perhaps we could use more filtering, perhaps not. This is an example with the mesh transition that's relatively abrupt, and we still see a reasonable similarity between the very high resolution simulation, which is repeated here from the last slide, and this one here. But if you were to compare with the other one, we're seeing more structure in here, which is suggesting that we're seeing somewhat more wave reflection and waves excited from that change in resolution when it's more abrupt, as opposed to the last slide where it was more gradual. And I can't really explain the lack of structure here, which was on the last slide. We're looking at that more closely. Finally, if we turn off the fourth order filter that was turned on in that slide, the last two examples I showed you, and just went with the Smagorinsky, here's what it looks like at low levels. You can see perhaps some spurious structure here, but it's not so horrible in the grand scheme of things. But this is only looking down low. Turns out if you look aloft, you'd see things that look very ugly, which is a suggestion of problems in the transition zone with wave reflection as things try to move out of this high resolution region. As noted, when one goes to using a background fourth order filter, a lot of that's essentially cleaned up completely. And I would note here that this value here on this 30 kilometer mesh, this is still about an order of magnitude below what's being used, for example, as the default value in the CAM course. So we're still at a relatively low level of filtering here. And part of this exercise is trying to determine at what levels we should set our filters by looking, in this case, at structures. We also look, for example, at kinetic energy and other things to determine the kinetic energy spectra. But now we're trying to look at the structures and just the eyeball test of what our solutions look like. Okay, so we've also done some real data testing, and I want to show one more set of examples that reflects that. We've gone back to a case from October 2010 that had, I think, really exemplifies what we see in scalar interactions. The dynamics of what was going on was that there was a very strong typhoon here in the Western Pacific. This was Meggy. It was one of the strongest typhoons ever observed, probably up until a couple weeks ago when there was an even stronger one that appeared. And it went across the northern Philippines and then turned north into China, into southern China. The outflow from Meggy interacted with the jet stream in such that it really strengthened that jet stream. So if you look several days after that, there was a very strong jet that came across and came across the U.S. West Coast here. Very, very strong winds, strong mountain waves, and lots of other weather. And then a couple days later resulted in one of the lowest surface pressures ever seen over the continental U.S. with this very, very incredible, huge baroclinic wave that wrapped up here. That was associated with a lot of severe weather and very, very strong winds here and weather and lots of mountain waves. So it was an interesting case. And also the very strong jet and the dynamics that developed should be a good test for whether our model is at least robust. So we're going to look at a few examples of results from putting the mesh, refined resolution mesh here over the Western Pacific, looking at the hurricane, the interaction here, and then another example mesh over the Eastern Pacific as the jet was impinging on here. And we're going to look at forecasts to see if we see any issues with the mesh transition here. So here's an example of the accumulated precip. On the top is from the Climate Forecast System Reanalysis. So that's an NCEP product. And the bottom, and this is for the mesh that's centered over the Western Pacific for the early part of that period. This is accumulated over 5 days, 20 October. So it has this is Maggie, the hurricane you see here. And as you can see, our uniform MPAS solution at 60 kilometers has that, as does our variable resolution mesh. And pretty much what you see is that the higher resolution region of the mesh here shows finer structure, but you don't really see anything untoward in the mesh transition region. The solutions actually look fairly similar, which is a good thing to see. But the accumulated precip is sort of like what comes out of the cow at the end. So you have to be careful. It's been through a lot, so it's worth looking at some other things. But before we do that, I'll show the same slide for later in that period for the west, the nest or the fine resolution region that's over the Eastern Pacific, and essentially you see pretty much the same thing. You see finer scale structure on the fine resolution region of the mesh, but you don't see anything happening in the mesh transition region, which in this case is in this region here. It looks very much like the uniform mesh solution and the CFSR solution here. So at least in terms of this particular metric, when we look at something we often look at is the precipitation, because that's really an important thing to forecast. We don't see very much of interest. If we look at more sensitive diagnostics, here's the relative vorticity. Here's at 500 hectopascals, think around 6 kilometers here. And this is the nest in or high resolution region in the Western Pacific. Again, all we see is nicer structure, but not too much. However, if we look up higher at 200 hectopascals, this is around 11.5 kilometers. Again, we see more structure here than we do out there, but I draw your attention to what's down here. This is structure that looks somewhat suspect, and it turns out it is. If we look at the vertical velocities at these levels, if we look here, we can see some problems primarily with perhaps the physics, and the convective parameterization is not doing quite what we'd like it to in the coarse mesh region, but in the fine mesh region, everything looks okay. We see, you have to look really hard, but we see maybe a little bit of what's going on down in this corner. It looks a little fishy. If we go to the mesh in the Eastern Pacific, we look in the same region, up at 200 hectopascals, we certainly see something here that is not very happy. And what I want to show you, we also see some signature of it in the vertical velocity field, although it didn't come out very well in this projection. If we turn on, that was just with the Smagorinsky, so we're really trying to back off and do the least amount of filtering we have to.
Are these 2 delta X things, or are they?
They're pretty close to 2 delta. I'd say that we're on the ragged edge here, that there's no doubt. But we're only using a Smagorinsky filter here. So when we turn on even a small amount of this Del 4 filter here, and this is actually well below what for example Cam would use on a 15-kilometer mesh, we can see that structure is just completely gone. And we've looked at other values. This is going up by a factor of 5, and this is by a factor of 5 again. And you can see we start losing some of the small scale structure here, and we're at the point now where we have to start looking and deciding what perhaps we want to use. But the scaling we're using, which is similar to what Mark described and is similar to what Todd described, is that we have to have these filters scale across our various resolutions smoothly if we want good solutions. So finally, I'd just like to end with what's going on with the Smagorinsky, which is what we have been running in a number of our NWP applications and our other models. And what you see here, this is a value of that filter coefficient, and the dark blues are low and the reds are high. That it's only turning on where of course the deformation is high. In these regions where we're seeing the noise here, and I point down to here, it's trying to do something, but it's just not clearly doing enough in any case. And in the simulations where we have this background filter on, now you can see that it doesn't turn on anymore, and now it really is confined to regions where the dynamics are perhaps saying that we we should be dissipating more. So I think this is where we're going to go with this filter, and some scaling along these lines. So to conclude, we've been doing some testing, and I haven't shown you all the testing, but this is just some highlights from it. Our original intent was to go only with the Smagorinsky filtering, but it's pretty clear that that's probably not going to be viable. And I think that's mainly because we no longer have any filtering from transport in our horizontal momentum equation. We've removed the horizontal transport and gone with this vector vorticity form. So we need something to effectively do that for us. So we're going to go with this fourth order hyperdiffusion, likely with a small value here to make up for the filtering we've lost. I think that obviously in these variable resolution simulations, the big game is going to be what we do with the other parameterizations, and we're waiting for our new computer at NCAR, and when we get there, we're going to start looking at simulations across the regimes from hydrostatic to non-hydrostatic. So thank you, and I'll be happy to take any questions.
So the region where you were seeing where you see the problems is in the coarse, on the coarse side. It's on the coarser side of the transition.
That's right.
Okay, so this isn't like kind of classic wave trapping, which tends to happen on the fine side.
It's not.
Then
I agree.
Can you characterize it in some other way?
No, at this point, no, but we haven't been looking at it that long. So whether it's a result of something that's particular to the Voronoi discretization, the TRIS method or not, it's not entirely clear. The idealized test I showed, the baroclinic wave with wave number 9, there the noise was in the high resolution region. That was a more classic issue. You can see we're seeing reflection and degradation of the numerics, and we need to take care of those small wave buttons.
Bill, in the, I guess you've run other experiments as well, right? In the other experiments, do you see any, is fourth order diffusion with Smagorinsky sufficient for all your test cases?
And I should say, we've been running with Smagorinsky for a long time, order a year and a half. And we've only really started looking closely at it. The model is stable with that noise in it, by and large. But it's obviously not dynamically it's not the solution we want. We want smoother solutions. Certainly.
Have you looked at higher order hyperviscosity or no?
Well, in the finite volume framework, we could go to higher order, but we haven't tried it at this point.
One comment on using Smagorinsky diffusion combined with fourth order background diffusion. We also have that option in ICON. And what turned out to be useful with that is to subtract part of the background diffusion coefficient then from the Smagorinsky diffusion in order to avoid double counting. So that's something you might also try.
One could. We have a stability limit on that Smagorinsky coefficient that has plenty of headroom for the fourth order filter.
But that imposes the upper limit. That's not what I mean. But when we combine Smagorinsky diffusion with the fourth order background diffusion, we then subtract an offset from the Smagorinsky coefficient that is proportional to the background coefficient in order to avoid double counting. So,
if you believe it's a physically based filtering, I think perhaps. I'm not so sure it's. Well, we should talk after.
Yeah.
I'd be curious as to what that shows.
Yes.
Bill, do you have any indication that by using the variable resolution approach from your runs that you've done so far, that you improve the medium range forecast over the US 3 or 4 days later or 5 days later?
Oh, geez, no, we haven't done any kind of forecast validation to look at metrics. What we can say is that the fidelity of the structures is greatly improved. But in terms of whether the forecasts are better, and really we need to get into a data simulation system. So we're going to be using DART and ensemble filter to start addressing those questions.
Yeah, so you were mentioning you thought that the continuously variable refinement might help with convective parameterization. You can certainly imagine mathematical formulas will vary continuously as you refine. But do you really think the physical problem is going to vary continuously as you refine? You can start with a 100 by 100 patch and want to parameterize deep convection in a 100 by 100 patch and then jump all the way down to a 20 by 20 patch. There may be some real issues.
Well, I didn't mean to suggest it was going to be easy. I think it will be easier than if you have an abrupt transition. Our experience with nests are that dealing with parameterizations and how they change across is very difficult. Whereas if it's smooth, I think we have a chance of designing something that works sort of adequately. That's about as far as I think I can go.
Maybe I'd like to bring up more philosophical point. For example, when we design a model, from the beginning, we tend to design based on like implicit, no dissipation, a shallow water result, analysis. And as I show in my presentation, in the real data simulation, we do need a dissipation. And actually, dissipation can change. For example, this geostrophic adjustment in the A-grid problem may be not so severe when you have dissipation. So you see, my point is, we based on implicit shallow water approach to design a model. But in the end, we need that dissipation. And that could change the analysis we base on. For example, A-grid, C-grid problem with and without dissipation. Could you comment on that?
Well, it's a travesty that we work so hard to construct these methods, these models, which are so accurate, and then we throw all its dissipation in. I agree.
Yeah, it's really, I know.
This is
many people
it's an unsatisfying
actually
thing.
happen. Yeah.
But when we go to full applications, we find we have to. And here, we're just trying to see how little can we get by with.
Yeah,
As we all do.
Yeah, I guess if you look into, but you are agree. Okay, thank you.
Okay, let's thank you.